talk about obstacle representation in configuration space, and it will the continuation of our previous lecture on where we define what is configuration space. So here we will briefly revisit the basic concepts and definitions, although we will pass a bit quickly. And then we will learn basic concepts like this Minkowski sum, its difference with Cartesian product, etc. And then we will take a very simple example of a regular geometric shaped obstacle and a regular geometric shaped robot. We'll also constrain by saying that the robot will not rotate, it will only translate. And within this restricted environment, we'll learn that how we can derive the equations of the half plane, which define the contour of a configuration space. And once we know the contour of a configuration space, the motion planning problem becomes easy. We can use any of our already known algorithms like discrete space planning algorithms. And when the algorithm is returning a point within the configuration space, we can only have to check that whether this point belongs to the convex hull defined by this half plane or not. If not, that is a free space. We can move the robot to that particular configuration. If yes, we cannot move that because it's within the obstacle space. Okay, so moving on. Again, we will require some prerequisites, that definition of this open set, manifolds, convex set, and Minkowski sum and difference. So the convex set and Minkowski sum and difference we will discuss in this lecture note. We discussed a little bit about open set manifold previously, and you can also read any standard book on mathematics or web resource, and also the textbook, this Stephen Lovell's motion planning book. It also defined these terms on the chapter 4. You can check this out. And today we'll first start with the examples of configuration space and definitions. So this will be a bit of repetition from our last lecture, but I will just quickly pass it through so that you can quickly contextualize. Then we will talk about the challenges and requirements for obstacle representations. And in that context, we will talk about Minkowski's sum and examples. And then we will take a very simple example of a one-dimensional case where the obstacle is also a straight line, the robot is also a straight line. And that will just show us that how we do the mathematical operation. And then we will take a 2D case where we will first discuss about the star algorithm, which kind of create an ordering of the vertices and edges, that at which order I should create the contour of half planes, and then we will calculate the contour itself. Here are the sources. These are similar to the sources that we discussed in the previous lecture, and the two main textbooks are this AI textbook by Russell Naufik and also the planning algorithm book by Stephen Lovell. So in this particular lecture, I will mainly follow the notations and examples given in the chapter 4 of Stephen Lovell's book. So motion planning in C-space, the basic steps are that we define the C-space, and the configuration space is defined as with one dimension part of the robot. We define the start and goal configuration, which is required for any of our path planning algorithm. And then we define obstacles, and to define the obstacles exactly, we use the star algorithm, which gives us the ordering, as we just told. And also there are approach there, in which case I need not to exactly derive the equation of the half planes, because for many practical examples, the obstacle can be of amorphous shape, or the robot has multiple DOF, making it much harder for us to visualize. So in those cases, we will learn the sampling-based approaches in the next class, like this RRT star type of algorithms. So this is a bit of revisiting of configuration space, that this is the also taught commonly in maths and physics lecture, that where we define the space which is defined by all possible configuration of an agent. Here we can also define configuration space of a point or a rigid body. So right side you will see some example of configuration space and how it take shapes based on this triangular robot. And in this lecture, we will actually try to find the equation of these half planes that constitute the configuration space for this triangular robot. And then we also talked about this task space and workspace in the previous lecture, that the task space is defined on the task. Mostly it's the Euclidean plane, and the workspace is we earlier discussed because it's easier to visualize. The workspace dimension will be at most Euclidean space. But as we discussed that if we solve the motion planning problem only in workspace, we cannot take into account the orientation of the agent. And that's why we move to configuration space, which combine both the translation orientation both together into a single space. So these are some example of C space of point object and robotic arm, and that for a free moving point, the configuration space is defined by this R cube, that the Euclidean space defined by the sets of real number. R is the set of real numbers. And if the particle is attached to a rigid linkage, then it can only move in a on the surface of a sphere. The radius is given by the length of the linkage, and the sphere equation is a square. And for a robotic arm which has n linkages, for each linkage we have the translation dimension by R cube and the orientation by this SO3. And if there are n linkage, the configuration space will be n dimensional on R cube and SO3. So one of you indeed asked that how we get this R3 into SO3 as a 6-dimensional space. So in the next slides, we will discuss that. So I hope you will, the concept of this Minkowski sum and Cartesian product of algebraic shapes or geometric shapes, I should rather say, will be more clear as we move on into the lecture. So this is again an example that we discussed in the previous lecture, that this is a robot, a very common robot that you can also buy as a DIY kit from Amazon or anywhere, where there are 2 motors and each gives 2 DOF. One is Q1 by the angle and Q2. And the configuration space is defined on the Euclidean space. Remember, this is I am not telling this is the XYZ workspace. This is the Euclidean space defined by the sets of real number. And here the robot's configuration space will be defined by this torus. And how we are getting the torus, we'll see in a second. And the robot can move only with a set of points on the surface of the torus. And the inner and outer radius of the torus will be determined by this linkage length L1 and L2. And we'll look into further detail that how we can also represent an obstacle on the surface of the torus or the configuration space for this simple robotic arm after a few slides. Now we will jump into the obstacle representation, which is the main topic of this lecture. So first we will learn this Minkowski set, Minkowski sum for sets. And Minkowski sum, that this snapshot I took from the Wikipedia. Here you can see I am just reading it out, that the Minkowski sum of 2 sets of position vectors A and B is Euclidean space is formed by adding each vector in A to each vector in B. So please note this addition operation. I will show you an example in a second. The difference with Cartesian product is that in Cartesian product, we do not do this addition. We define the state as Cartesian product by taking one element from each space and take another element from each space. We do not do the summation. So yeah, this Minkowski is best known for his foundational work on describing space and time for 4-dimensional space, Minkowski space-time, which facilitate the generic interpretation of the general theory of relativity, where space and time is combined together and used to more accurately measure gravitational effect combining with the time. So if you probably I discussed a little bit about this space-time and theory of relativity in very superficially in some introductory lecture, but it's interesting to note that this combination of space-time in Minkowski's sum and difference was later explored for making more famous invention. So this is a more rigid example, and I hope that your this confusion about that how we get this higher dimensional space will be further clear. That here, say we have this position vector A 1 0 0 1 0 minus 1 and B 0 0 1 1 1 minus 1 here. And how I can get the Minkowski sum. So here this plus denotes Minkowski sum, not our general addition. And it is like that I take this first element and add it to the second element and get 1 0. Then I take the first element, take the second element and add it. So for a Cartesian product, we do not do this addition and we get this 2 1. And so we go along 1 0 1 minus 1, we get 2 minus 1. And then I pick up the second element, the 0 1, and we continue the process 0 1 and 0 0, we get 0 1, 0 1 and 1 1 give us 1 2 addition. 0 minus 1 and 1 minus 1 give us this 1 0 and so on. So how we doing the additions in the later example, you will see that when here the addition means that vector addition, that will be further clear to you as we look at more examples. But also you can look at this right side picture where you can see the lines define the contour, and it is finally how many points? There are 9 points. Among these 9 points, 3 points are same, especially this 1 0 points. You can see it appearing 3 times here, which is the center point. So the rest 6 points constitute this contour of the hexagon, and the other 3 points designate the center of the hexagon. So again, you can see these examples in Wikipedia, and we will use the very similar example for defining the half plane in after a few slides. Okay. So let us first take the very simple example of 1D case. 1D case means that here both the obstacle and the robot is aligned. So the robot is in all subsequent slides, as I'm telling that I am using the notation in the Stephen Lovell's book, that the robot will be represented by this A symbol and obstacle by O. So the robot A is spreading from -1 to +2. Obstacle is spreading from 0 to 4. So the obstacle space will be defined by this Minkowski's sum or difference O minus A, or the sum of O and the negation of A. So the negation of A will be just, you can put minus here, and it will be like as if I am translating it one step. So it will move to this, -2 to 0 here. And then I will add them just as we did this Minkowski sum in the previous slide. And this is the obstacle space. So the Euclidean space will be represented by this R, the set of real numbers, which is spreading, say, maybe -infinity to +infinity. Within that, -2 to 5 is the obstacle space. So the robot cannot move within this space, and all the other space it can move. Okay, so this is looks a bit trivial, but this is the basic definition that how we will going to use it. And as soon as we will make it a 2-dimensional space, it will look a bit more complicated. So let us see that how we actually define the obstacle space in 2D. So this is a 2 image processing operation, this dilation and erosion, and they use the Minkowski sum and difference. So in this case, you can see that as I was earlier describing, that say the robot is a circle, okay, and I just drag this circle along this edge of this obstacle, the square, like this, and I draw the contour. The contour will be, it will have this rounded edge due to the structure of the circle, and this operation is known as the dilation operation, and the erosion is opposite. Erosion is that I am, instead of the outside of the obstacle, if I move the circle inside of the obstacle, what I will get. So that is the Minkowski's difference or the erosion operation. And same thing you can see here, that how if I have a triangular robot and a rectangular obstacle, how the obstacle space will look like using the similar notion of Minkowski's sum and difference. Okay, so this will be the obstacle space, and very soon we will find the equation of these lines. Before doing that, we will just define this term convex set. So by definition, a set S is convex if and only if every line segment connecting 2 points in S is contained within S. So in this case, say this is not a convex set because this part of the line, if I just use a different color, that this part of the line is outside the shape. Similarly, say this part of the line, or in this case, if I draw a line here, this part of the line is outside the shape. So these are not convex shape. But in this case, the first example is convex set. And why we are talking about convex set, that we can define the convex hull with a set of points, and this convex hull will be an enclosed space containing these points. So in the previous examples, as we are talking about, that basically what we are doing, that we are defining a set of half planes or a set of points, and we are drawing a convex hull across this using these half planes or points, which is defining our obstacle space. So in this case, we will just again define two more terms, which maybe we will not use much in this lecture, but it is important to know this holonomic constraint. That this holonomic constraint results from the physical restrictions that make it impossible for the robot to enter some region. So say, for example, like in our elbow joint, that I cannot touch the back of my arm, because the constraint given by the type of the joints on our elbow. While the non-holonomic constraint, this does not only depend on the structure of the robot, but it also depends on the way the robot is moving. So the best example is the inability of a car to slide sideways to a parking point. And it's often difficult to work with non-holonomic constraints because it can arise from the system dynamics. So, for example, a vehicle moving at 5 miles per hour can easily make a 30-degree turn, but cannot do that at a higher velocity. So for holonomic constraint, we can encode the holonomic constraint, and they are not going to change based on the task or situation. They are remaining same. So I can define the obstacle space considering, say, the linkage structure. But it's more difficult to do it for non-holonomic constraint because there we have to also take into account of the task. So it's I just wanted to make you aware of these definitions. We'll not use them much in the remaining section of this lecture, but for practical examples, this is something we should be aware about. And mostly for fixed base bots, we will only deal with this holonomic constraint. But for moving bots, again, most of the cases we will stay at holonomic constraint because most of our moving bot will move very slowly in indoor space. But if we are doing something, say, for semi-autonomous vehicle, then we have to also consider this non-holonomic constraint. So this is the basic 2D case. So in the subsequent cases, we will consider a triangular robot. We will also consider this, the triangular robot will not rotate. It can only slide or translate. Our obstacle is also of a fixed geometric shape of a rectangle. And as you can see that we are sliding this obstacle across this, we are sliding the robot, across the edge of the obstacle, just as we discussed in this dilation and erosion operation a few slides ago. And we are trying to find the lines, these lines, which are defining this obstacle space. So we will actually derive the definitions or the equations of these half planes in the subsequent slides. So our workspace will still remain in the XY coordinates, this, and the configuration space will be defined by this union of the obstacle space and the free space. Okay. And if we also allow rotate in the 2D space, so then you can see that for a particular value of theta, this will be the configuration space. But if I change the theta or orientation of the robot, the configuration space will change. You can see these two pictures. But when we will derive the half plane equation, we'll do it for a fixed value of theta in case. But if we can do it for a fixed value of theta, we can also extend it for other values of theta. So next slide, we will show that how we can also do the configuration space for, say, multiple obstacles. So in this case, there are two obstacles. One is a rectangle one is circle one. And exactly by the similar principle, by sliding this triangular robot across the obstacle surface, we get two different obstacle space. Okay. And a valid path will be that in previous lecture, we discussed about the problem with cell decomposition, that some cells may have mixed cells. That means the cell contains both obstacle space and free space. But if we know the exact equation of the obstacle space in terms of these half plane definitions, we can make a motion path which is going in between these two obstacles. So that will be one advantage of defining the obstacle space accurately instead of fully discretizing it. Okay. Example of this two-DOF robot whose configuration space is represented by these theta 1 and theta 2, these two angles. And in this figure, you can see that the configuration space will be a 2D space and represented by these two DOF, theta 1, theta 2. Here we are taking two obstacles. So one is a square shape and a circle shape. And this is how the configuration space will look like in a 2D. So we also use the color coding to represent this square and the circle. Again, how we are exactly getting this shape, that we have to mathematically calculate, and that is also difficult. In subsequent examples, we will take more easier shapes and easier types so that we can hand calculate that. But if we represent the configuration space in 3D, it will be look like a 3D, or yes, it will be look like a torus. And this line is where this theta 1 is equal to 180 degree. And if we cut open this torus and make it flat on the surface, we will get this shape. And on the surface of the torus, you can see that we are getting the obstacles like this. So any motion planning will be finding a set of points on this torus surface, just like here. That here we have 2 points, Q1 to Q2. So this is angles. These are not Cartesian XYZ points in robot workspace. These are the joint angles. And this is how the robot will move actually when we are doing this motion planning. So the robot cannot go from here to here. That means from it, this arm cannot reach here due to this obstacle. And that's why you can see in the configuration space that it is divided into two parts. Now I ask this question that this is this Cartesian product of two shapes or two sets. The S is this circle, and the Cartesian product of two circle will be a torus, not will be a sphere, as it looks like from our previous knowledge of algebraic multiplication. And the reason is that the Cartesian product of two manifolds means for every point on one of them, we will put the other circle. So here, if you see that this line is theta 1 equal 180 degree, and I have put another theta on every point of this circle. That's how I get another circle. Or the other way around, that you can consider we start with this circle and then I put the other circle on every point of this circle. So as if I took a small circular rubber band and move it across a circular bangle. So the result will be that based on the radius of the rubber band, I will get the width of the torus and will result in a torus. So that's how this is. We sometimes got confused because we learned multiplication on scalars or later on matrices. But here we are talking about by this multiplication symbol, we are meaning the Cartesian product. Okay. So next we will discuss this star algorithm. So this is the standard algorithm that how we can exactly define the contour of a configuration space. And in defining the star algorithm, what we will do that this is more a generic definition or generic steps that we will first consider both our obstacle and the robot or agent. They have fixed algebraic shape, okay, and which we can represent by say straight line. In later case, we can relax this definition, but for the time being, we will consider them. They have a regular geometric shape, and we will define the normals on each of the edge which constitute the robot and obstacle. So this normal will make an angle of inward edge normal in counterclockwise order. So we'll consider a specific order, and similarly we'll draw normal to the obstacle as well. And then what we will do that we will order these normals based on their angle, because we are taking on counterclockwise direction like this. And we will consider this normal one by one, and each normal will constitute one half plane, which will define the obstacle. Let me show you with example. So here we, in the subsequent example, we will use this triangular robot. Again, I am using the notation from Stephen Lovell's book, chapter 4. That we will take the example of this triangular robot, and we will also assume that this robot is not rotating. So in practical life, maybe the robot will rotate and we will have a higher order configuration space than the 2D plane that I am showing on the slides. But just to explain, we will make this restriction. Similarly, we will take a very simple rectangular obstacle, and these are the outward normals from the obstacle, and these are the inward normal. Normal means this is right angle. I think you could understand that. And then with respect to say this horizontal axis, I will order them in counterclockwise direction. So alpha 1 here, then beta 4, and then so on and so forth. So total, you see there are 1, 2, 3, and 7, 3 plus 4, 7 edges, considering both the robot and obstacle. So our configuration space will also consist of 7 half planes. And in the subsequent slides, we will try to find out that how we can find these equations of this half plane. So before doing so, the star algorithm only tells us the procedure, that how we should proceed to find this half plane equation. It's not exactly telling us that how I am calculating the half planes. So this is a pictorial notation. So we will exactly follow the similar principle that say here we will start from this position, and the robot is moving like this. And you can imagine that I am trying to, like in class, we use the physical example that I am trying to move the chair across the table and making sure the chair will not hit the table. So if I want to draw a contour, what I will do, I will touch the chair with the table surface and drag it along the whole circumference of the table and make a contour across that. And when I am moving the chair, I will make sure the chair is not crossing that contour, because if it crosses that contour, it will hit the table. So as long as I am outside that contour, I will know that the chair will not hit the table. Similar principle that you can see that we are basically dragging it along the surface. And since the robot cannot rotate, so at this case, what I do, that I am dragging the robot along its edge. Okay, so here I am dragging the robot across the edge of the obstacle, but here I am dragging the robot across the robot's edge. And similarly, we bring it back to the starting point here. And then I getting this 1, 2, 3, 4, 5, 6, 7 half planes, which is defining the obstacle space. Now our next task will be how we can find the equations of these half planes. So before we proceed to calculate these equations of half planes, we have to classify the types of edge. Again, here we will assume that we are working in a 2D plane and we have a simplistic robot. Later on, we can relax this criteria. So we will define two types of contact between the robot and the obstacle. One is the EV, where we are dragging the robot across the robot's edge. So we are giving priority to the robot. So when we are dragging the robot across its edge, we will tell it EV type of contact. And when we are dragging the robot vertices across the edge of the obstacle, we will term this V contact. Okay, V stands for vertex, E for edge, and we are giving the first letter denotes the robot. That's why EV means I am dragging the robot across its edge, and V means I am dragging the robot across its vertices along the edge of the obstacle. So the basic principle is that the motion vector of the robot as it slides around the obstacle should be perpendicular to the vector normal to the surface of the obstacle in VE case. And EV contacts contribute to N edges of the C obstacles, one for each edge of A. Okay. So again, we will see that how it is actually happening. Now, this is how we are proceed towards finding the half plane equations. That here you note that we take the normal. So these are the outward normals. These are the inward normal. So when we will drag the robot along the edge, so we will define a vector. One is the normal, and another will be the, say, the movement vector, the V. So when it will be, so maybe I will first go to this picture. So this is the velocity vector, and here you can see the angle here. Okay. But when it will touch the surface, this velocity vector will be at a right angle with the n vector. So we can just write n dot v equal to 0, something like that. So same thing we are doing here, that we will use that equation and we will consider in the subsequent point this coordinates of point P. So as we will see that in this example, we will consider P as the center of the robot. And with respect to that, we will find the half plane equation like using this principle. Okay. So finally, we will, after that, we will get a polygon with n plus n edge, where n is the number of edge of the robot, m is the number of obstacles. So, and we will separately treat them that when based on the type of the contact. So again, still now it can look to you a bit abstract still, that how exactly we are doing that. But we will show that with an example. And I also find that it is much easier to explain with example rather than keeping on going notation. So this we already seen that how we are getting the equation of the half planes. So this is, we will deal with this vector v and the normal n, and we will have to find out the equation of this normal. Now, before going into that, I will just, I am sure many of you remember, but I will just talk about a little bit of vector notation. So just consider this is 0, 0. Okay. Sorry. And say this is a point 1, 0. So if I now draw a vector like this, so this vector I can term at, say, something like 1, 0, or I can, sorry, or I can just write it something like T0, where T is a fixed scalar multiplier. Similarly, say this is the line where it is, say, 0, 1. So I can draw a vector here like this. And I can write it something like 0t, where t is a scalar multiplier, or I can just write the notation 0, 1. Now say I have a point, say somewhere 1, 2 here. Say this point is 1, 2, or maybe this point is 2, 1. Okay. So now if I try to draw a vector like this, similarly, I can write its notation something like that, say 2, 1, or by a fixed multiplier, 2t and t. And then I can find the equation. I will just, sorry. The defined color that I can find the equation of a normal vector with respect to that. And again, that I can write that I know this slope. It's easy to calculate here. And this slope will be this big angle, that 90 degree plus theta. And from that, I can, maybe the equation will be that 2t minus t, something like that. Okay. Yeah. T is the scalar multiplier. Yeah. So see, if I just take another point, say, I'm just say another vector, that what is, say, t and 2t, that this is 1, 2 point, just imagine. So similar principle, I can also find its normal across that by negating the second one, the t minus 2t, or we can write it, the notation, we can write the lines notation will be 1, 2, and maybe the normal will be 1 minus 2. Okay. So I think it looks a bit clumsy, but this is the basic vector notation we will use. Okay. So this is our picture that we start with. So this is the same triangular robot. I now zoomed in, and here you can see the coordinates -1, 1, 0, 0, 1. And this is the first position of the vector, sorry, the robot. So here the robot vertices A3 is touching the B1, B4 line, this line. So this is a V type of joint because the, sorry about that. So this is a V type of joint because the robot vertex will drag along the edge of the robot. Okay. So the robot vertex is A3. You can see on the top row. Edge is before B1. The robot is going in this direction. Okay. What is the normal? So this is the normal. I will just use a defined color. So this is the A non-normal. And here the P is the center point. So why I am writing 2, 0 here? Because you just see the robot's position here. So the robot's center is 0, 0. So yeah, the robot center is 0, 0. This is 1, 0. So now the robot's A3 is here. So where will be A? 1 coordinate here. So this is 1 minus 1. That's why it will be 2, 0. This is 0. So x. So this is 0. Y coordinated 0 and x is 2. Okay. And we saw this xt 1 plus, if p is in a few slides before, we see p is 1, 2, it is 1 plus xt, 2 plus yt. Using similar notion, based on the direction of the vector, we are going upwards. We are getting the half v as xt minus 2 and yt. Yt, and basically yt minus 0. Here, this based on this point 2, 0. And the half plane equation will be xt minus 2, 0, which will be this vertical plane. Okay. Here. This one will be this line. And next we will drag the robot across to the B1 edge where the A3 vertex will touch, now drag along the B1, B2 surface, this direction. And here, again, the vector normal will be 0, 1, this vector. Here, it will be 0, 1 as we saw just before. And the position of the point will be 2, 2, this center point. So sorry, this will be the, just 1 second. I'll just move this point slightly this way. Yeah. Okay, so this point A will be at 2, 2 now. So this is just dragging across this line, okay, this half plane. So this will be at 2, 2, and the V equation will be xt minus 2 and yt minus 2. And from that, we are getting the half plane equation as yt minus 2 less than equal to 0, which is this line. And then the robot will come to the point B2. Okay. Now things will be a bit more complicated. How? Because from V joint, I will now come to a EV joint. That is not the main complication. But the complication is now the normal. So far the normal was with respect to the obstacle's edge. Okay. And the obstacle was nicely centered at this point. So we are just getting the rectangular lines for getting the normal. But now the normal will be inward facing. So the direction of the normal will be this way. Normal to this line, A1, A3 line. And this A31H, because the robot will now drag across this way. So here we exactly as we show before, we tried to show you that how I get this normal equation. So if you look at this line L1, its slope is how much? 2 unit by 1 unit. So tan theta formula 1 by 2. And I can write the equation as something like, say, T 2T. And then the equation of the normal, you can see this angle will be pi by 2 plus theta. So if I consider the normal just as another vector, I can find the slope as tan pi by plus 2 theta, which will be minus cot theta, what is minus 2, 1. Or from our known dot product notation, I can write that if the vector is T2T, the normal will be T minus 2T. Okay, basic vector notation. And that we are writing as the normals as 1 minus 2 using our notation. So using that, we are getting the n as 1 minus 2. And similarly, we are using the location of the center point A. And from that, we are getting the half plane equation as minus xt plus 2t minus 4 equal to 0. So this is just algebraic calculation that you can find and which is giving us this line. So after this position, this 1, 2, 3, 4, now the robot will again drag along the edge of the obstacle. Sorry, let's get the pen. Edge of the obstacle. So again, we will from EV will come to a V type of joint. And again, B2, B3 we will take this normal. This normal is minus 1, 0. So this is minus 1 and 0 this way. And the position of A, the center point will be minus 2 and 1. Again, you can see the notion that this is 1 positive direction Y and negative direction left hand minus 2. And we can find the V equation is by multiplying that minus 2 into 1 and 1 into minus 2. So we are getting this similar formula minus 62 minus yt. And from that, we are getting the equation for the next one. This is the normal is minus 1, 0, and we are using this value of A and getting this half plane equation. Now here there was some discrepancy what given in the Laval's book. I checked it with some students and senior faculty. So the half plane equation, we found it to be minus xt minus yt minus 3 less than equal to 0 for but I just would like to report the discrepancy. And after this, the robot will similarly move across. Yeah, this edge is the minus 60 minus y2 minus 3, not the previous one. And this way we finally reached and get the whole equation. Okay. So this way we construct the obstacle and find the half length of the obstacle. So although it may sound complicated finding the half plane equation, but if you follow these steps and I kind of do it step by step, you will find the see that it's not that difficult for this simple algebraic case with regular shapes of obstacle. So next, what happens that if we don't have are working on a 2D plane that we have say 3D obstacles. So in that case, we define 3 types of contact. One is a face of A and a vertex of O, like our EV. Then a vertex of A and face of O, that is like our V joint. And then there will be a third type of joint where, since these are 3D robots and obstacles, that one edge of A will drag along one edge of obstacle. And we will define the plane equations based on these 3 types of contacts. So as you may now see that it's will be a bit difficult to exactly find this half plane equation for different types of obstacles. So then what we do in the next class, we'll learn that these sampling based approaches, in which case we will have these modules which will sample the configuration space and return to us that whether I can go to that place. And this collision detection will work as a black box, that it will not find the exact equation of the half planes or the planes or hyperplanes for a higher dimensional place, but it will just give you the yes no answer that whether your robot can reach a particular configuration or not. And we'll learn into detail of that. And this will be the main takeaway point, that in this last 2 days, we learned that what is basic configuration space and how obstacle is represented. We took a very simplistic use case of a triangular robot without any rotation and a regular obstacle and find the derivation of the half plane equation. And in that context, we also look at a little bit of basic maths in terms of Minkowski sum, this vector processing or the Cartesian product, etc. We learned the star algorithm, which orders that in which way we should find the half plane equations. And we look at these obstacle contour formulations, equations. It may look complex, but if you follow the slides, you will see that step by step equations of it. It's not that complex. So with that, I will stop recording. So